In today's class, we will learn a new classification technique called backpropagation. So we will cover a part of neural network here. We will see that how we can train our network so that whenever we are successful to train our network using my training data set, then whenever a new data comes or a test data comes, then we can successfully predict its original class, right? Means where we have to map it. So let us see how it works. So firstly, we are going to see that how it will work. We will see different methodologies used here, and at last we will see an example that how we are going to implement our neural network to classify the data. So here a neural network is a learning algorithm. Okay, so whenever we will proceed with our lecture, you will see that as the time proceeds or in each iteration, my network is going to learn from the training set. Fine. Training set means, just to recapitulate, remember we are in supervised learning technique, right? So here for any input set or for any input, there will be a corresponding output. So to begin with the process, we are having both input and output mapping. We know for this particular data item or for this particular input item, it is going to have this output. So we are having the standard input output set with us. Now whenever we will build a model, we will see that whether my model is predicting correctly, right? Means whenever I am feeding the same input, is it going to give me the same output value as we know or not? If it is not giving the same output value, we have to train our network more, right? So how we are going to train our network more, how it is going to develop itself, or how it is going to learn, and then it is going to minimize the error rate, or means rather we have to abolish the error rate, but in actual scenario we have to minimize it. Okay, the error rate should be very minimum, and we have to learn that how my neural network is going to learn. Okay, so what here we will see that a neural network will have a connected input output units, and there will be some weight associated with it. So if you remember that, we know when we are going to associate some weight in my graph, say we are having some having 4 nodes and each node is connected by edges. Now whenever we associate some weight in my to my edge, right, that means we are giving more priority to that edge, right? That means that edge will have a maximum effect, means it will vary with the weight associated to it, right? So whenever the weight is more, that means its contribution to the network will be more, and if it is lesser, so its contribution will be lesser. So in that fashion we have to find out that how we are going to give weights to the input between the input and output units. We will see it. So during the learning phase, and the network will learn by adjusting the weight. Let us say we are having 4 inputs and we are using that. You will see there will be different layers. I am not going to that now. So for each input, say we are combining different inputs and we are generating some outputs, and for that set of inputs we know that what will be the actual output. Now if after combination it is varying in a greater range, that is what is my output, means what is the output generated from this network and what is the original output. If the difference between them is more, so we have to adjust the weight accordingly so that the output generated by the network is very close to the original output, right? So that is a learning phase mainly. So we will see that how to adjust the weight, what are the different procedures available, and these are the proven procedures. So we are going to follow this while solving any numerical problem in our course, right? This is also called connectionist net learning, because there are connections between units. So connections between units, from this sentence, this connectionist learning, has this word has been generated. So this is not used so oftenly, but still better to learn all the names as well. Fine. So before entering into this, we will learn some weakness, but you will see that okay, it has some drawbacks, fine, but it has many more advantages as well. So it's a very important technique, or it's a very famous technique which we can use as a classifier. So weakness is, first weakness is, this is the most important drawback of neural network. The training time is very long. You can understand that whenever my data set will be very huge, and we are trying to map them so that we can generate output, and after that we are tallying whatever the output is generated by the network with the original output, and whenever this output varies in a range, we are going to adjust the weight so that we can come very close to the original output value. So this continuous changing of weights, or continuous updation of weights, is a long process actually. So the training time, that means the building of model time using the training data, or trained data rather, so this is consuming a lot of time. So for a huge data set, it works fine, but the time consumption is more. So it requires a number of parameters, typically best determined empirically, that is the network topology or structure. So here you will see that whenever we will learn this technique in detail, you will see there that we are going to develop a network topology. So network topology, in the sense, you will see the concept of three different layers here, and from the input layers we are going to combine them. That two has no defined rule, but rather it according to our need we have to map them. So that mapping structure, or that mapping function, we have to define of our own, that which inputs we are going to combine to build a output set. So that topology, so whenever we are going to build a topology, so there should be a satisfied number of parameters, so that we can train our network in a efficient manner, right? Or it should give very accurate values. Okay. Third disadvantage is poor interpretability. So this network is having a problem of it faces difficulty to interpret the symbolic meaning behind the learned weights and of hidden units in the network. So here actually whatever we have seen so far, that in case of decision tree or in case of naive based classifier, you have seen that they were very easy to understand, they were very easy to implement, but here you will see some symbols which we are going to use. So whenever we are going to debug the meaning of it, it is little bit difficult to interpret the meaning of those. Fine. So these are the three disadvantages, but strengths are more, definitely. It has high tolerance to noisy data. So this is the I think for data mining, this is the most quality should be there for every classifier, right? So if it cannot tolerate noise, means if it has the tolerance level is not high for noisy data for any classifier, so it cannot build up model successfully, right? So because since we are collecting data from different sources, so the chances of noisy data in my total data set is definitely higher. So there should be defined procedure to tolerate with the noisy data, so that how we are going to handle our noisy data, that's a major concern, right? Here ability to classify untrained patterns, means it can classify very neatly and with very effectively, right? So this is one more most required quality of any classifier. It is well suited for continuous valued inputs and outputs, right? So if whenever you will see, there will be no need of converting the continuous valued input to discrete valued, as we have seen in the last two classifiers which we have read for our syllabus, that is decision tree and naive Bayes classifier. That okay, whenever we are going to work with continuous valued attributes for decision tree, there is a if you remember, we were finding out the intervals and we were calculating the midpoint value, and then somehow we were trying to map our continuous valued attribute to the discrete values. Otherwise we cannot map it to the this kind of classifiers, that is decision tree or naive Bayes classifier. But here you will see, in case of neural network, it is capable enough to handle both kind of inputs. Using the same network or using the same algorithm, you can do it for both type of data. Okay, successful on an array of real world data, handwritten letter. So whenever this kind of classification scenario comes, that we have to predict the we have to work in such a input scenario where the inputs are handwritten letters. Okay, it is not machine written, it is not typed, and they are handwritten. So it is difficult to study for any kind of classifiers, but neural network can handle it very easily. Algorithms are inherently parallel. You will see that when the total training process, whenever we are feeding all the data to the network, it's it is undoubtedly a parallel process. So here the time consumption occurs also when okay, it consumes a lot of time in training to train the model or to build the model, but still it is again it can work in parallel as well. Fine. So we will see pictorial representation of this one. For now we will not understand whatever is written in the box, leave it for now. We are going to learn it, how to develop that formula, how we are going to use that in classification problem. Just we will move from bottom to up. Okay, just see the input vector. Input vector, if you remember, for a particular attribute there may be a set of input symbols, so that will be treated as the input vector. Okay, so we have remembered that if we denote any attribute as a suffix k, then say it has it may be of the 4 length vector, so there are 4 different input symbols. So here we are working with 2. Now you can see here there is a concept of input layer. So the total data will be fed to the input layer first, then you can see that there are some mapping kind of thing, right? And in between layer comes called hidden layer, then output layer, and then output vector generates. Fine. You can see here that whenever the input vector is having only 2 attributes, the output vector is having 3 attributes, but this is not fixed. You can change it according to your need. You can increase it as well. Now, what is the job of the hidden layer? So this hidden layer is going to map, this hidden layer is going to rather combine different input symbols, so combine the inputs from different input layer set, and you can see here one weight parameter is associated to it. Okay, so every edges, whatever you can see here, will be associated with an edge, with an weight, and we will see how to generate the total given input vector and its corresponding output vector. We will learn it using the example. Okay, so this is the total structure. Now you can see here there is only one hidden layer, so as per our requirement there can be lot of hidden layers. Okay, so here we are mapping in some fashion. We can change the mapping and build a second hidden layer. We can again change the mapping. So in this fashion we can increase the number of hidden layers as per my need. So here we will learn that what are the different layers and how each layer acts. That is our goal. Then we will see the example. Okay, so now you have seen that the inputs to the network correspond to the attributes measured for each training tuple. These inputs are fed. Then these inputs, whatever we have seen that they are directly fed to the input layer. Okay, so each layer can be made up of any number of units. So whatever inputs we are getting, we are feeding it to the input layer having different units, and then weight is associated to the edges going out of the input layer, and it is being fed to the hidden layer. So you can compare it with the flow chart or the diagram just mentioned in the slide before. Okay. And the number of hidden layers is arbitrarily, but usually only one hidden layer is used. But do not stick to this one. For any real life problem, we may use any number of hidden layers. Actually, you will find there are more than one number of hidden layers in most of the cases, but there must be at least one hidden layer. We have to remember that. But for our syllabus, we will restrict ourselves to only one hidden layer, because we are learning just very basic concepts of neural network. We are not going to cover the total neural network syllabus here, because our goal is to learn this neural network as just a classifier. We will just learn the basics of it. Okay, fine. So the weighted outputs of the last hidden layer are inputs 2 units making up the output layer. So if we revisit the slide, previous slide again, you can see here that the weighted outputs means whatever the the output hidden layer is generating by combining the inputs from the input layer and the weight associated with it. So with this, whatever it is going to generate, if there are more than one hidden layers, so the output of the first hidden layer will be fed to the second, the output of the second will be fed to the third. So if it proceeds in this manner, the output of the last hidden layer will be fed to the output layer only, right? So based on the total whatever my last hidden layer is generating, my network will predict accordingly, right? So whatever the last hidden layer is going to give to the output layer, my output layer is going to map accordingly. So the hidden layer should be designed in a very effective way. So that is our main learning phase. So whenever we will come up with the output set, we will compare that with the original output of the trained data. If it varies, then we have to change the or adjust the weight accordingly. We will see that how we are going to adjust the weights. Okay, and this network, you can see easily that it is totally feed forward. There is no backward tracking, right? So whenever we are moving forward, that means we are going to move forward only, we are not coming back. So that's why it is totally feed forward network. Fine. Now whenever we are going to define a network topology, we have to decide a few parameters. First is, that is the number of units in the input layer, how many input layer we are going to keep in our rather how many input unit we are going to keep in our input layer. So in our example, we have kept 2 input units, so it may vary, we have to decide it. There should we have to decide how many hidden layers to keep in the total network topology. At least the value should be 1. Okay, and if the requirement is more, we can increase the number of hidden layers. Then the number of units in the hidden layer, we have to decide it as well. In our case, it was 3, so it may be 3, it may be more than 3, it may be less than 3, whatever the requirement is. Okay, and lastly, the number of units in the output layer. And we have to normalize the input values, and this is the most important factor of training any model, or for data mining, we have to normalize all the value. That why? Because if we use different ranges of values, so the values with the higher range will always have the higher priority, so we cannot build our model correctly. Okay, so it will have a biased nature. So to make it unbiased, we have to normalize the value first. Then discrete valued attributes may be encoded such that there is one input per domain value. Okay, so per domain value, in the sense, say we are having different different parameters based on which we are developing our network. Okay, so if we can encode our value, that means, say it's a student parameter, which we were using the example of buying computer or not. So a person is a student, yes or no. So if we can encode in this fashion of 2, means if we can make it a binary if we can bring it back to 2 class classifier, okay, That means for each and every parameter there will be two set of outputs. So if we can maintain in this fashion, so then there can be one input unit for per domain. So one input unit will be enough, right? So whenever we are giving one input to it, either it will be yes or no, the decision will move accordingly. So we can do it like this. Now for example, which I was talking of, say for an attribute there are three possible or known values. What are those? These are, say, A0, A1 and A2. Now if we assign three input units to represent A, so why we are using three input units? Because you can see there are three possible known values. So if these input units are I0, I1 and I2, you can easily see that whenever my A0 holds true, then what I am going to do? Means whenever A0 is true and other are false, then what will happen? My I0 will be active and other two will be inactive, right? So I0 will be set to 1 and other will be 0. Similarly, whenever if A1 is active and A0 and A2 are inactive, then I1 will be 1 and rest will be 0. If you remember that in our example there was an attribute named income, so it had three different values. One was low, another was medium, another was high, right? So if we can for this attribute, if we can maintain three input units, so whenever the low value holds, that means the high and medium will be 0 and the low value will be 1. So for medium, other two will be 0 and medium will be high. So in this fashion we can build the network, we can define the network for for discrete values of attributes. Okay, now here neural networks can be used for both classification to predict the class level of a given table and the numeric prediction, right? So say when for classification purpose, our general goal is to find out which class a particular input belongs to, or we can, for continuous valued attribute, say we are trying to find out a numeric prediction, that we are giving one value, so in which range my value is going to fall. So in both the cases we can use my neural network. Now for classification, means for the first case, one output unit may be used to represent two classes. How is it possible? So if we keep one output unit, say for our case, for purchasing computer or not, so output class is what? Either it will buy computer or it may not buy computer, right? So one output unit will be enough, right? Either it will be yes or it will be no, because both cannot occur at the same time. So one output unit will be enough to use it for two different classes. When it may be true, it may not be true. So whenever it will be true, that means my decision is positive, and whenever it is false, my decision is negative. And if there are more than two classes, then one output unit per class is used. So say there are two different choices, say say it may buy computer or it may buy video game as well. Okay, so there should be, for each output value, there should be one unit defined for each one of the decision. Okay, so once a network has been trained and its accuracy is unacceptable, then we are going to repeat the process. Okay, so that learning procedure we are going to learn here. So whenever we have built a network, and we are going to do what? We are going to tally whatever my network is generating, the output generated by my network with the original output. So if it varies, we are going to make some changes to the network. So now what is the why the term back propagation? Right, so here it is doing what? It iteratively processes a set of training tuples and compares the network's prediction with the actual known target value, which I am talking of so often in this lecture, because that is our main goal actually. So whenever we can compare with the actual target value with the whatever my network is predicting. So that target value for the for classification will be the class level. That means, say, we know if this condition holds for a person, he is going to purchase the computer, and if this holds for a person, he or she is not going to purchase a computer. So whenever we are feeding those inputs to my network, whether it is getting labeled correctly or not. So if it is somehow misclassification occurs, then we are going to retrain my model, or we are going to adapt my model, or make my model learn more, right? And for continuous value, it will have the numeric prediction. So here weights will be modified. That is the only learning phase. So we are going to modify our weight. We will modify one more thing, that is bias. We will see it later on, but for now that we are going to modify our weight. So how we are going to modify it? We have to minimize the mean squared error. Mean squared error, we know it is a defined parameter to measure the error rate, right? Mean squared error means, say my output value is whatever the output generated by my model is varying with at a certain range from the original output value. So mean squared means we will make the mean of each of the errors, and we have to square it, right? So that why squaring is required? Because we are going to keep the absolute value only, right? So here you may mean square it, you may find absolute, but mean squared is a standard procedure. So we are not going to find out the error may be at the positive level or at the negative level. That means if say my original value should be 5, so it may be say the output generated is say 10 or say 2. So whenever we are subtracting 5 from 10 and 5 from 2, the chances of negative and positive values in the result is there. So we are going to discard the sign. For that we will use the mean squared error, right? Now modifications made in the backward direction from the output layer through each hidden layer down to the first hidden layer. So this is the back propagation. So whenever we will visit the example, you will see that some error will be generated, and whenever we are going to find out or whenever we are going to adjust the weights of the edges in such a fashion so that by error rate minimizes, so we are going to backtrack it, right? So from the output layer we will find some edges are there coming out of hidden layers. There will be some weights associated with it. We will first adjust those weights, then come to the hidden layer, then from the outermost hidden layer we will come from right to left, and we will keep on adjusting the weights, and ultimately we will adjust the weight going out of the input layer. Okay, so that is why the name is backpropagation. Fine. So the steps involved in backpropagation are step 1 is initialize the weights. So firstly, to begin with the process, we have to initialize the weight. So arbitrarily we will fix some weights ranging from -1 to +1, or from -0.5 to 0.5, right? And this is small random numbers will be generated. So accordingly, first we will initialize it, and each unit has a bias associated with it. Whenever we will move to the later slides, you will see what is the need of bias and how we are going to use it in predicting the class level. And then biases will be similarly initialized, and after that, whenever one iteration completes, we will see where my error lies, and we have to modify both weights and the biases. Okay, now this is done. So initialization process done. Now how the training phase or the training will occur? So it is 3-step function. We are going to learn each step in details. Before that, we will see just what are the 3 different steps. First is propagate the inputs forward by applying activation function. We will see it. Backpropagate the error by updating weights and biases. Again we will see that, and there are some terminating conditions. So we will see what are the conditions when we can terminate. So let us begin with the propagation of inputs forward. You can see here what is being done. here the first the training tuple is fed to the network's input layer. Okay, so input layer means, so the training tuple, let us say the input layer is having the value of say y1, y2, yn, right? So these are the values of the input layers. Now the input passes through the input units unchanged. You can see if you follow the first diagram which we have seen, whenever the input units are there, it is directly fed to the input layer, so there are no changes in it. And then for each input j, its output oj is equal to the input value ij. Since we are not changing anything, so the input and output remains the same. Means whatever we are feeding to the input layer, the output coming out of it are same. Okay, so next input and output of each unit in the hidden and the output layers are computed. So that is our main goal here, that how we are going to feed the outcome of the input layer to the hidden layers, means how we are going to match them, how we are going to make the mapping. Okay, and based on that the input to the hidden layer will be processed. So how we are going to combine different input layers to feed those outputs to the hidden layer, and by after applying the weights to it, that will be the input to the hidden layer. Okay, now net input to a unit in the hidden or the output layers is computed as a linear combination of its input. You will see whenever we will see the example that there will be a linear combination. Say if our this diagram is considered, so whenever we are going to find the weighted sum, it will be like y1 multiplied with wij, then y2 multiplied with w2j, in this fashion. So whenever we will do a linear combination of inputs. Now each such unit has a number of inputs to it that are in fact the outputs of the units connected to it in the previous layer. So as the number of hidden layers increase, so the output of a previous layer will be considered as the input of its own, right? So my input will be, for the case of hidden layers, whatever I am getting from my previous layer. So each connection will be associated with an weight, and so as I was talking of, each input will be multiplied with its weight to calculate the weighted sum. Now see here, this is the formula which we follow. You can see that for each input unit, right? So for ij, you can see here that the net input will be wij multiplied by oi. Oi means the input of each, the output of each input layer. Okay, so each input is not layer but unit. So the total input layer, the total weighted sum, as I was telling you, that it will be calculated like y1 multiplied by w1j, then plus y2 multiplied with w2j, in this fashion. So this y1, y2, yn are what? The output of each input unit, because the input of each input unit and output of each input unit are same. That's why the output of each input unit which we are feeding to the layer, that will be multiplied with the weight associated with it. And a bias is there, so bias is required, because we will use that bias to maintain the threshold. Okay, so if we can maintain a threshold value, say if the total output generated from this input layer is not up to the mark, and thus that bias will be capable of deleting it. Okay, so here you can easily predict that my bias, if we can maintain we have to maintain the bias in form of negative sign. That means whenever we are calculating the sum of a particular input unit, or sum of we are finding out the weighted sum, and say if my bias is -1, so if the total sum value cannot go up of -1 value, then the value will be means it can be deleted, right? So it will have no effect in the total value, total summation, whatever we are generating. So to maintain a threshold, that whether we are going to consider this input as effective or not will depend on the threshold. That's why this bias is maintained. Then you can see here, and then each unit in the hidden and the output layer takes this total input, and an activation function is applied to generate the output. The activation function you have seen there, we will see that one logistic activation function we will use here, that may differ, so you may design other activation function as well, and that activation function will be used to generate the output. Okay, and just see, this is the activation function. This function we are going to use to generate the output. So it is 1 by 1 plus e to the power minus ij. So we have calculated the value of ij, so if we just place it in this formula, we can find out the output. Okay, now here one more thing is done. So whatever the output each unit is generating, right, so whenever we are accumulating the all, it is coming under ij, but before that we had got different output values coming of each unit, so we are going to store them, because we have to back propagate to change the weights, and again we have to calculate these values. So in that situation we will require these values as well, so we have to save it in cache. Okay, now the next step was back propagate the error. So we have to find out the error, we have to back propagate to minimize the error. Now just see the formula of ERRJ. Do not focus on the first part. See, the difference between the error is Tj minus Oj. That means Oj is the output generated by my network. You have seen that we have calculated the Oj using the activation function that was used here, and then and my target value is known to us because we are working with the training data set, so we know what will be the actual target value. So if we subtract my original value or with the value my machine or my model is generating, so we can find out the difference, and from where this Oj multiplied by 1 minus Oj is coming, it is the derivative of the logistic function. Okay, so if you find the derivative of the logistic function Oj, you will get this one. So in this fashion or using this formula, the error is calculated. Okay, so remember this is the error ERRJ. Now if we have to calculate the total error, so what we have to do, we have to find it for each and every value, that is, so if ERRK is the error generated for each unit, right, so using the formula which we have seen before, we can find out it. So if ERRK is the weight generated by each unit k and the weight associated with it is wjk, so if we can find out the sum of all these fashions, that is error multiplied with its weight for each of the unit, and can find the sum of it, and then we can find out the total error generated by the hidden layer. So this is the way in which we can calculate the error generated. Okay, now back propagate means what change we need to do. You can see here for this changing of weight is denoted by delta of wij, and we know the error, that is Ej of Oi, the total error generated, and here we will introduce a parameter called learning parameter. So whenever we can multiply my error value just with a rate, it typically lies between 0 and 1, so it can be any random value. So these are the proven theories. Okay, so we are not going to prove it, but we are going to learn it only. So if we can multiply that error generated with a learning parameter or learning rate, then the total change in weight which we want to we have to do, that will be stored in the change, small change, right? That's why delta wij. So the weight will be updated accordingly. See the previous weight, if it is wij, then we have to sum it with the changes, that is delta of wij. Similarly, the bias will be changed, right? So this is the same formula. So we had our previous bias that is theta j, and we are maintaining the change in the delta theta j. So if we just sum it off, then my new bias will come. Now the last phase, that is the terminating condition. So these are the termination condition. So what are the condition when we can stop? If all delta w of ij in the previous step was so small that it falls beyond the falling below the threshold. So whatever changes we are making, then the total change in the network is not so effective, right? So then it means if we can maintain, again if we can maintain that, okay, this is the threshold. So if delta wij is above this threshold, that means the changes should be a little more, right? So if this much of change is required, then we are going to retrain my network, otherwise we are going to stop. And again the percentage of misclassified in the previous is so less that we can discard it easily, or we can even restrict the number of iterations as per my need. So this can be three different stopping parameters. So this is the example which I was talking of. We are going to look at this example. You can see here there are 3 input units, that is 1, 2 and 3. 2 hidden units, that is input or 2 units in the hidden layer, that is 4 and 5, and 1 output unit, that is 6. So you can easily see then x1, x2 and x3 are the 3 training tuple, not tuple, 3 vector training tuple denoted by x, and we are having some weight associated with it, and so we will see that how it is going to work, and we will assume learning rate to be 0.9, right? So what my this example is going to come up with, it is going to we will learn that how to go on with the back propagation steps, then how to find out the net output and input and how they are compared, and we will calculate the error, we will calculate the weight and bias updates, and means we are going to do all the things which we have learned so far. So these are the values given, and all the calculated values as well we have calculated. Just look at the first table. Here we are working with only one training example. You can try it for any combination of x1, x2, x3, but remember to restrict it with the value of 0 and 1 only, okay? So because we are working with true false value. Fine. So the first training data is x1 value is 1, x2 is 0 and x3 is 1, okay? So the weights are given. W1 4, that is the age between 1 and 4 is having some weight, and all others are having some weight, and 3 biases are also given, that is theta 4, theta 5 and theta 6, okay? Because you can see 2 hidden layers and 1 output layer is there, that's why 3 different thresholds are required, okay? Now whenever we have to calculate it for the unit 4, that is the hidden unit 4, so what are the different inputs it is having? It is getting one input from x1, it is getting another input from x2 and one more input from x3, okay? So fine, and the weight associated with 1 and 4 is W14. So x1 multiplied by W14, it is 1 multiplied by 0.2, so 0.2. Then x2 multiplied by W24, that is 0 multiplied by 0.4, that's why 0. Then x3 multiplied by W 34, right? So 1 multiplied by W34 is 0.5, minus 0.5, that is minus 0.5, and what is the bias of it? Minus 0.4, that is theta 4's value, right? So this is coming to minus 0.7. So if we have to calculate the output, you remember that it is 1 by 1 plus e to the power minus ij. So it will be 1 by 1 plus e to the power 0.7, it is coming to 0.332. So similarly you can calculate it for 5 and calculate it for 6 as well, okay? So before calculating 6, you can easily understand we have to have the value of this W. Okay, we are having all the values, that is W46 and W56 as well, so we can calculate it. Now using the formula of ERRJ, we have seen there, you can find the ERRJ for each of the unit. Okay, so there will be, just see, when we are calculating the error, we have to back propagate. That means we have to find out the error occurred at node 6 first, then we will use it to the errors occurred at 5 and 4. Okay, next we will calculate the changes which we need for the weights. So again, whenever we need to change the weights, we have to backtrack. Firstly, we will adjust the weight. That is how we are going to adjust the weight, the original weight plus the changes in the weight which we have, that is the delta wij, which we have calculated using ERRJ, using the error value. Okay, just take a pen and paper and just verify whether these are correct or not. I have taken the sample from the ebook which we are following only. Okay, so this adjustment in weights are calculated. Again, the adjustment of biases are required, so again it has been calculated. So using this, again, what we can do, we can reiterate. So if you just take any example and try to map it in this fashion, you can predict how much accurate it is. Now, how we can classify an unknown tuples? We have trained our network, fine, but now we are going to test it. Okay, we are going to use the test data. So what we are going to do to classify an unknown tuple X, the tuple is input to the trained network and the net input and output of each unit are computed. So here, in case of testing phase, definitely you are not going to calculate the back propagation error and all, because that is a training phase only. So whenever we are going to test for a new data, we are going to calculate the in the trained network, we will feed it, and it will from the input unit, it will move to the input layer, then hidden layer, and ultimately the output will be generated. Okay, fine. So in this fashion it can be used for the testing purpose. And if we have to stick to the efficiency of this, so this is the efficiency of back propagation, and if d are the number of tuples and w are the weight, so it will take order of d multiplied by w, and this is the total time complexity it takes. And rule extraction, sometimes before building this total network, there's some pruning process is also carried out. Say some of the attributes or some of the input features are very less relevant, right? So we can discard it before building the network. And if we have to analyze the sensitivity, we have to see that the how much the particular input variable is having the impact to the total network, and the total knowledge whatever we are gaining, it can be represented using different rules. You have seen in case of decision tree, we have used some mathematical features to represent the total outcome which we have generated from the network. Means we have considered the true values only, and we have built it using the OR and symbol. We have represented the total logical expression, right? So using the mathematical logic, we have represented the total working principle of the tree. So similar thing can be done in this neural network as well. So with this we are going to end up today, and in the next class we will cover one more topic of a very important classification technique. You can see that there will be some situations when none of this will be capable enough to classify the different data tuples, but then we will use the support vector machines. We will see how it works. Thank you for today.